Welcome to CPE 350 Chapter 6.3, the second portion, Visualizing the Error Function. This is supplementary content. You do not need to understand how the error function is defined in order to use it. This is just for your information. So the error function, as we discussed previously, is defined as an integral of a solution that does not have an analytical value. And this is quite similar, actually, to the expression for a Gaussian, which you'll probably recall from a statistics class long ago. If we look a little bit more carefully at our Gaussian, we remember that the area under it is equal to 1 because it's a normalized probability distribution function. And so the way we write that is the integral from negative infinity to infinity of the Gaussian equals 1. Now, for the Gaussian I've shown here, we've already decided that the average value, mu, is equal to 0, which is why it's centered on the y-axis. But we'll also choose that the standard deviation equals 1 over root 2. And so if we plug that into our expression for the Gaussian, that means that the roots 2 cancel. And now, if we integrate this expression for the Gaussian from negative infinity to infinity, it will equal to 1. But it's also starting to look a little bit closer to our error function. No surprise. The last thing we'll do is note that the Gaussian is symmetric about y equal to 0. And so that's to say that the area on this side of the curve is equal to the area on the other side of the curve. So those two areas are equal. And how we can write that is from negative infinity to 0, the integral has the same value as from 0 to positive infinity. So those two integrals are equal. Now, if we want to use the integral here on the right side, and we're going to choose that because it looks a little bit closer to our error function, if we plug that into this equation, we have to multiply by 2 because 2 of these equals the whole area of the Gaussian, right? Which is equal to 1. So now we've got an expression that looks very much like the error function. The only difference is that this expression, the limit of integration, the upper limit is infinity, whereas for the error function, we let it vary. From this, though, we can assess that when you let y equal infinity, the error function has a value of 1. And then kind of by inspection, if you let y equal 0, you're not actually performing an integral at all, and so the error function is 0. And that's why those are the ending values. But let's look a little bit more at where the error function emerges from graphically. So this is our function e to the negative y squared, which has a Gaussian shape, but it's not actually a Gaussian because it's not normalized. We have to divide by the square root of pi in order to normalize it. And the reason, again, that we normalize it is so that the area under this curve is 1. So the area under here, if you integrate from negative infinity to infinity, which is numerically pretty much the same as negative 3 to 3, for this particular example, you'll get a value of 1. Okay, so that's our Gaussian. And now let's actually perform that integration. So if we integrate from negative 3 to 3, the blue Gaussian function here, what we get is this green curve, which is the integral. And so the integral is not changing much in this region. It's changing very slowly because the Gaussian is changing slowly. It starts to increase rapidly in this region where the value of the Gaussian is quite high, and then it saturates in this region. And again, it reaches a value of 1 as expected because it's the integral of a normalized Gaussian function. Okay, this integral is quite similar to our error function, but not quite, because the integral is, again, going effectively from negative infinity to positive infinity on the y-axis, whereas the error function, we've chosen to define it from just 0 to infinity. And so our error function basically resembles half of the integral for our Gaussian, but it's also normalized so that the final value of the error function is 1. And this is just a sort of a convenient way of translating the integral of a Gaussian into positive coordinates only. So the error function, roughly speaking, is the area of a Gaussian. And that's where it comes from.